Okay, guys, what we're going to do right now is take a look at some of the in-class practice answers you guys are working on today or should have worked on, and then you'll have a chance to work on some homework for some more further practice. Um, the steps for drawing the Lewis structures are here, so it's really important to follow those. If you ever get stuck, it gives you the step-by-step breakdown of what you need to do. I'm going to go through the practice example answers really quick, but I'm going to do a quick example myself first that involves all of these steps. So we're going to look at CO2. So step number one is to count your valence electrons. Students always think they're too cool, and they don't do this because they're in honors chem and they think, oh, I don't need to count electrons. I'm past that. You're not. I tell my AP kids, you're not past that. You must count them. That's where the easy mistakes are made. So first thing I do is look at carbon. Carbon has 4 valence electrons. Then I look at oxygen, and oxygen has 6. But there's 2 oxygens in there because it's CO2, so I have to double it to give me 12. So I have a total of 16 valence electrons here. Okay, so what I need to do is follow my steps and start with my skeletal structure. So I'm going to put the least electronegative element in the center, or it's going to be the element that makes the most bonds, which is going to be carbon that makes 4, or it's going to be use common sense. Okay, there's only 1 carbon. Well, okay, that's going to go in the middle. Put your oxygens around the outside. You don't need to worry about the correct shape just yet. You'll learn about that in a future lesson. But then we want to put single bonds from the central atom to each of the surrounding atoms. So let's do that. Single bonds count as 2 shared electrons. Okay, so we have 2 shared electrons here, 2 shared electrons here. They're kind of moving around those regions, kind of holding the carbon and oxygen together. Look at how many electrons we've used so far. Each single bond counts as 2 valence electrons, or 2 electrons, I guess. So we've used up 4 electrons out of our 16. We have 12 left. So what you want to do is put the rest of your valence electron pairs around the outside first. Okay, so don't start on carbon, start on the outside elements. You're going to start on the elements with the higher electronegativity, which is oxygen here, because higher electronegativities want electrons more. So I'm going to put them around and we're going to count. Okay, that oxygen now has an octet. That's again what we're trying to do here. So we have 8 electrons around this oxygen, and we've used up 2, 4, 6, 8, 10. 10 electrons so far. Let's give this oxygen an octet. Okay, count up your electrons. You have 2, 4, 6, 8, 10, 12, 14, 16. Fantastic. We need 16 electrons. So it looks like we're done. However, step 5. If not all of your atoms have an octet, swing in an unshared pair to form a double or triple bond. So these lone pairs on oxygen here and here belong solely to that oxygen. Okay, so this oxygen has 8, this oxygen has 8. So those are good. This carbon though in the middle only has 1, 2 from that bond, 1, 2 from that bond, 4 electrons total. We need 8. So what we can do is like we can't just do this. Students do that all the time, and that goes back to what I said. They think they're too cool to count electrons. You should have 16. They're like, oh, easy. I'm just going to give everything an octet. I'm just going to live my life and do it that way. Well, then you're going to get lots of points taken off because if you count your electrons now, the structure as written has 16 electrons or 20 electrons in it. Okay, well, you're not allowed that. You're only allowed 16. So do not, under any circumstance, do what I just did. Okay. So I can try to erase those. All right. What you want to do instead is swing electrons from the outside in. So I'm going to pick these 2 electrons right here on oxygen, and instead of having them belong solely to oxygen, let's make them belong to carbon and oxygen. All right. So that's going to create a double bond here. And the previous video from the lesson, it showed you how to do this. So here's another 2. I'm going to move them in there. Okay, if I just moved in 1 lone pair to the center, carbon still wouldn't have an octet, right? It would only have 6 valence electrons. Let's clean this up a little bit and see what the answer is. All right, carbon in the middle, double bond to oxygen, double bond to oxygen. You had the single bond already. You moved a lone pair in, okay? You moved a lone pair in. Now that lone pair belongs to carbon and oxygen. That lone pair belongs to carbon and oxygen. Now look, carbon has an octet, 2, 4, 6, 8. Okay, 8 electrons around carbon. Now oxygen I'm going to put those lone pairs back. Okay, so it had 1, 2 lone pairs, so I moved them down. 1, 2 lone pairs, moved them down. So this, okay, is your final answer for CO2. It doesn't matter where you put the electron pairs. You see, I went rogue here and moved them. That's not a big deal. All right, so this covered all these steps. Do not make double or triple bonds for the fun of it, okay? You only do that when your central atom is electron deficient, you don't have an octet, and you can't use up any more electrons, right? We only have to have 16 total, and we have 16 here if you count them all up. There are exceptions to the octet rule, which are group 13 elements, like boron, aluminum, gallium, and you can make expanded octets as well, up to 6 pairs. Okay, we'll talk about that in a little bit. Let's look at one more example, BH3. So BH3 is boron trihydride, and we're going to count our electrons. So boron has 3. Hydrogen has 1, but there are 3 of them, BH3, so that's 3 electrons total. So add them up. I need 6 electrons for this whole structure. So let's follow my rules. Element that makes the most bonds or least electronegative in the center. That's boron. Now put your other atoms around the outside. So I'm back to this step here, okay? Draw the skeletal structure and put your single bonds in. Let's do that. We have 3 hydrogens. Yes, I ran out of room, sorry. And I put my single bonds in. Okay, let's count electrons. I have 2 electrons here, 2 electrons here, 2 electrons here. That is 6, okay? So guess what? I'm done. Boron's an exception. Any group 13 element is an exception. They can have an octet, but they're okay without an octet. So this is actually a valid Lewis structure here, and we're done. Do not go lone pair happy. All right, students do this all the time as well. They just put lone pairs on everything. You're like, okay, everything has an octet, and this makes my blood pressure go up because I only need 6 electrons, and you have like 6 million. Okay, that's too many. So you want to make sure you only have the number that you are allowed to have in your structure. So hydrogen will never have anything other than a single bond. This will never happen in a bajillion years. So you want to make sure you keep track of your electrons. So pretend all these lone pairs are not here. This is the wrong answer. I had the right answer just a second ago. Okay, let's go through these examples really quick and we'll see what the answers are. So we have H2S. I'm not going to go through everything step by step here, but hydrogen has 1 valence electron, and there are 2 of them. Sulfur has 6, so that gives us 8 total. Okay, sulfur's in the middle, bonded to hydrogens. That takes care of 4 of our electrons. We do not put valence electrons, like extra ones, on hydrogen. So we leave that alone. So we move to our central atom, right? Hydrogen is okay with just 2 valence electrons through that bond. So I have 4 electrons here. I need to use up 4 more. And I am done. Okay, lovely. That is my answer for H2S. So sulfur in the middle has an octet. Hydrogen is cool how it is. Life is good. All right. We're going to draw these a little bit later next week or the next lesson or two, and we'll look at the proper shape. This is not how this is normally going to look. This will actually be a bent shape, but that is for another day. All right, PCl3, do the same thing. So P is phosphorus, has 5 valence electrons. Chlorine has 7, but there's 3 of them. That gives us 21, so do math, and we get 20. That's a 26. Just take my word for it. Okay, central atom has to be phosphorus. 3 chlorines. Single bonds for all of them. Sorry, this is kind of sloppy. Okay, that takes care of 2, 4, 6 electrons. Now let's go through. We have a lot left. Let's go through and put our outside valence electrons on first. Give chlorine octets. Sorry about the sloppy octet or valence pair here. That's how it is. Okay, count them up. we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, well, that's not good. I need 26 electrons, so we'll put 2 more on the central atom. So if you go back to your steps, you do the outside atoms first. I cannot stress that enough. Then you move on to the inside if you still have electrons you need to use. Everything needs an octet except for our certain exceptions, right? So if you count everything up, you have 8 valence electrons on everything. You have 26 electrons total here. This looks fantastic for PCl3. Okay, again, this is the wrong shape. This will actually be a pyramidal shape, but we'll cross that bridge when we get to it. Next one, H2O2. Students always get hung up on this one. We're going to put oxygen in the center. You always put, like, hydrogen will never be in the center, ever, 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 okay? Because it only makes one bond, which we've seen a couple times already. So you have to put that on the outside. We have 2 oxygens, so we'll put them in the middle, and let's count our electrons. 1 for hydrogen times 2 gives us 2 total. 6 on oxygen times 2 gives us 12. That gives us a total of 14. Okay, let's go through and put our electrons where they need to go. I'm going to move this over a little bit so we have room. Okay, so oxygen, oxygen. Everything likes to be relatively symmetrical in chem, so put 1 hydrogen on 1 oxygen. And put 1 hydrogen on the other one, all right? This will be a weirder shape, but don't worry about it yet. So we have 2, 4, 6 electrons in use so far. I need 14, so I have 8 left. What I need to do here is I can't start on the outside because hydrogen is good, okay? It has its 2 electrons from those single bonds. So what I'll do instead is move on to my inside atoms and go to oxygen. So I have 2, 4, 6 electrons so far. That's 8, 10, okay? That's okay because I have an octet now. So I have 2, 4, 6, 8, 10, 12, 14. Okay, lovely. So oxygen has an octet, good to go. I need 14 electrons total. Each hydrogen only wants 2. It's satisfied through that bond. So I have 2, 4, 6, 8, 10, 12, 14. So I am done. All right, H2O2 is hydrogen peroxide, which I've done some demos with earlier. Okay, moving on. This one's in your notes. It gives you the general structure already. So it's C2N2. Okay, I'm going to connect it all with single bonds first. Let's count our electrons up. I need 4 from carbon, but there's 2 of them, so that is 8. And nitrogen has 5 times 2 gives me 10. I need 18 electrons total. All right, so I have 2, 4, 6 in my structure so far. So following my rules, start on the outside, work your way in. I need 18. I have 6. Let's keep going. Okay, so I have 2, 4, 6, 8, 10, 12. 14, 16, 18. Those are my 18 valence electrons. You're going to say, well, I'm done. And I'm going to say, no, you're not, because you need to follow your rules. Everything needs an octet here. There are no exceptions to the octet rule in this problem. So carbon needs an octet. Nitrogen's good, okay? I cannot, right? Not just go rogue, okay? Okay, look, I'm done. Everything has an octet. Well, guess what? You added 2, 4, 6, 8 electrons too many. So again, you are not cool enough to skip this step where you count your electrons. Don't get cocky about this. You want to make sure you actually follow the rules and don't exceed the number of electrons you are allowed to have. So what I will do here is try to erase this annoyingly. All right, there we go. What we're going to do is swing electrons in from the outside. Okay, so let's take a look at how we do that. All right, so let's swing those electrons in and we'll wrap this up. Okay, so let's move in 2 electrons from there into the center. Now you can look at carbon here. Okay, carbon has 1, 2, 3, 4. If I move those in, there'll be 5, 6. There'll be 6 electrons on carbon. I still need the octet, so I'm going to swing in another lone pair. Okay, swing that lone pair in, and now I'll have a triple bond. Okay, I'm gonna do the same thing on the other side. This carbon only has 1, 2, 3, 4 electrons attached to it. I need 4 more. Swing in that lone pair, so it goes from just nitrogen to belonging to carbon and nitrogen. Same thing on the bottom. Okay, swing those in, and let's see let's see what this would look like at the end when all is said and done. Okay, so that takes care of it. So you can see the triple bond here. I had the single bond, in the middle there from my original structure. I swung in 2 electrons, made that one on top, swung in 2 more, made that one on bottom. Now look, nitrogen still has 2, 4, 6 from that triple bond, plus the 2 lone pair, right? The 2 from the lone pair, that gives us 8. That's an octet. Carbon has 2, 4, 6 from the triple bond, plus that single bond, giving us 2 more, that's 8. Same thing on the other side. Carbon has 2, 4, 6 from the triple, and then 2 more from the single, that gives us 8. Nitrogen has 2, 4, 6, 8. 2 from the lone pair, 6 from the triple bond, and we're good. Okay, that's kind of as tricky as it really gets here for some of these. If you add up your electrons, you have 2, 4, 6, 8, 10, 12, 14, 16, 18, and you need 18 electrons. So again, you don't want to just go lone pair crazy here on the central atoms because you won't have the right number of electrons. So that's how we do some triple bonding. Last one, SF6. Let's knock it out. We have sulfur having 6 valence electrons. Fluorine has a million, so it's 7 times 6. Okay. 6 times 7 is, I have no idea, 42. Is that a true story? I don't know. Okay, so we add them together, 42 and 6 gives us 48. Okay, let's go to work. Sulfur in the middle, obviously. 6 fluorines around the outside, so let's figure this out here. Okay, so those are going to be my 6. Okay, so I've taken care of 2, 4, 6, 8, 10, 12 of my 48 electrons. That leaves me with a lot left. Let's just go through. Everything needs an octet here. Let's just go for it. Okay, let's see if this is like real. So we have sulfur in the middle, and then a single bond, and then a fluorine with 6 electrons from a lone pair. So this fluorine has an octet. All of them do. And let's just do some quick math here. I have a fluorine with 3 lone pairs and a single bond. 8 electrons from that times 1, 2, 3, 4, 5, 6 times 6 of those. 6 times 8 is 48. And I'm good to go. All right, so that takes care of this one. You're going to say, well, I'm breaking the octet rule. And there's sulfur in the middle here. So we have 1, 2, 4, 6, 8, 10, 12. That could happen. Okay, now here's the last thing for this quick review. If you go back to our rules, a million slides ago here, if everything has an octet but more electrons are needed, you can put them on the central atom. Or if you just look at the one that we had, like sulfur had 6 bonds, right? It had no choice. It was SF6. What this means, only the elements with d orbitals can have expanded octets. So we could pile away those extra electrons in the d block. Well, remember, the d block doesn't start until the 3rd level, right? We don't enter the d block until we have 3d whatever. So this goes all the way back to the electron configuration information that we learned. So if you look at sulfur on the periodic table, sulfur is in the 3rd period, okay? Is in the 3rd row, right? You would have sulfur's configuration end in 3p4. 3p4. So because sulfur is in the 3rd level, you can have an expanded octet here, okay? You cannot have an expanded octet for anything in row 1, so that's hydrogen or helium, or row 2, which is lithium all the way through neon. Those will not be allowed to have expanded octets. okay? So you can only pile away those extra electrons in the d block, and that doesn't start till the third level. So if you have an element from sodium all the way through number 118, oganesson, we'll never use that, but you get the idea. They are allowed to do what sulfur did, okay? Row 1, row 2, not allowed. I hope this helped have some of this make sense for you. You can work on the homework, which is the next 2 pages in your packet, where you'll do more practice with this. We'll do this a lot, okay? We'll do this when we do VSEPR theory and polarity, and as we progress through the unit. This is the foundational skill we need to have. So hopefully this makes sense. You guys have this, and good luck on that homework. If you have any questions, you can let me know. We can deal with it then. All right? Sounds good.